Hello everybody. In this video we're going to talk about where in real world you're going to see a hyperbolic function. I mean, in your calculus you probably have seen a sine hyperbolic of x that was basically an exponential function, right? Something like this. Or if you change this sine to cosine hyperbolic, then it would be this plus, correct? And you might say, where would I see something like that in the real world? And today I'm going to show you. So here I have a cable hanging from 2 points by its own weight. So there is no external load on the cable, just its own weight, which is not negligible. And we want to find if the equation of this curve is y equal f of x, what kind of function is that going to be? Or what is the differential equation governing y versus x? Okay? So let's take a look at that. So here we consider the weight density of the cable to be mu. So mu is weight over length. And if you look at the previous video I had on suspension bridges, the governing equation that we derived for a small element like this was basically this guy. D of t naught tangent theta was w dx, where w dx was the vertical force. Now here, there is no w, but this length, if you consider it ds and mu is weight per length, then this force w dx is to be replaced by mu times ds. So here, this is going to be what? Like this. And if you divide by a t naught, which you considered it constant, you will get d of tangent of theta is equal to mu ds over t naught. And you can also divide both sides by a dx. So it becomes like this. Okay, so this is going to be what? This is going to be the new thing we have. D over dx of tangent theta is mu ds over dx over t naught, and that's what you can see right here. Now remember that theta was the slope, so tangent of theta is the first derivative dy over dx. If I plug it into that equation, this is going to be that governing equation. Now still, this equation is not a perfect differential equation because there is dy dx and ds in it. So I have to get rid of ds to make it all based on y and x. And here, remember, for this small element, again, if I go back to that picture, for this small element, ds, it has two components. One is this length, dx, and the other one, if you look at this small triangle, and the other one is this one, which is dy, right? And since it's very small, this curvature is negligible, so you can say ds is like the hypotenuse. So ds squared is dx squared plus what? dy squared, and that is this one. From here, I can find ds, right? So basically, first divide both sides by a dx, and take a square root. If I do that, so I divide both sides by a dx and take a square root, you'll get ds over dx to be what? To be the square root of 1 plus dy over dx squared. Okay, so this is what? This is this term that I'm going to replace. And if you do that, you get this equation in the red box. This is your governing equation, all based on y and x. Clearly, it's second order, and clearly it's nonlinear. Now, can I solve this second order nonlinear ODE? Yes. How? First, we do a change of variable and call the first derivative p. If you do that, this is going to be dp over dx on the left side. And on the right side, you have mu over t naught square root of 1 plus p squared. Here you do a separation of variables and you get this guy. And then you will what? You will integrate this. The integral of this mu over t naught becomes the linear function plus, of course, a constant. And this left-hand side is a natural log, like that. Now at x of 0 at origin, the slope, here is origin, the slope or p is 0. Therefore, this constant c is going to be 0, right? Because at x of 0, this term is 0. And when p is 0, this is 0, this is 1, and natural log of 1 is also 0. So this whole thing is 0. So c is going to be 0. Right? So the c is gone. So now you're only down to what? You're only down to basically this equation. Now you use exponential for both sides and you get the argument here, p plus square root 1 plus p squared is exponential of the right hand side, which is this guy, so you get this equation. And now here you have to solve this for p because p is not explicitly given as a function of x, it's implicitly given. Actually, this is a quadratic equation in terms of p and x, right? So you have to solve this for p as a function of x. And in order to do that, what you need to do is to bring this p to this side so it becomes negative p, and then you square both sides. If you square both sides, what will you get is 1 plus p squared on the left, and on the right you get e to the 2 mu x over t naught, and then plus p squared, then minus 2 times p times that exponential term, right? Mu x over t naught. Now these 2p squared would cancel, and then you fix this. Then this 1, you can bring it to this side, and that negative 2p, you take it to the other side. And then divide both sides by what? Divide both sides by 2 times this exponential. So it's going to be this exponential squared minus 1 divided by exponential to the power 1. So you get 1 power of exponential, and 1 divided by that is going to be a negative exponential, and both divided by 2. So you get this guy. And what kind of function is this? Yes, it's a sine hyperbolic of mu x over t naught. So your first derivative now, p, first derivative, is a sine hyperbolic function. And of course, if you integrate both sides, then y is the integral of sine hyperbolic, which is a what? Which is a cosine hyperbolic, plus a constant like this. Now at x of 0, y is 0, right? At x of 0, y is 0, so that constant k is determined, plug it back, and you get y as a function of x. So finally, we could solve it, and you clearly see what kind of function we have. There we go, cosine hyperbolic. So yes, the shape of a cable under its own weight hanging from 2 points is a cosine hyperbolic. There is another name for that function, that curve, we call it the catenary curve. So if you ever hear the word catenary or catenary shape, that is this cosine hyperbolic. Okay, a few more things that we need to talk about is this t naught that we have in the equation of y versus x. This constant t naught is an unknown. Okay, we have to find this guy. So it depends on the boundary conditions we have. So far we have used the conditions only at the bottom point, where at x0 y is 0 and also dy over dx is 0, but we also need these endpoints. So here at x of L over 2, y is h. So if I plug that in into the y versus x equation, I'll get this guy. And if you look at this, this is an algebraic equation, but it's nonlinear because t naught is here and in the bottom of that, in the denominator of the argument of cosine hyperbolic. So if I want to solve this, assuming that I know h, mu, and L, if I want to solve this for t naught, it has to be done numerically. Okay, there is no analytic solution to this. So I need to find t naught what? Numerically. Now, if somebody says, what's the length of this cable in this specific case where it's symmetric and it's a little bit simpler to calculate, then we use the length of the cable that I had in my previous video on the suspension bridge. Still, this equation is valid. This is always valid as long as it's symmetric. And now for this derivative of y versus x, remember it was p, it was the sine hyperbolic function. So I plug it in, and you know 1 plus sine hyperbolic is a cosine hyperbolic squared. So 1 plus sine squared hyperbolic is cosine hyperbolic squared. Under a square root just becomes cosine hyperbolic. And integral of cosine hyperbolic is a sine hyperbolic. Now sine hyperbolic at 0 is 0. At L over 2, that's this parameter times 2. So clearly you see that the required length of the cable is what kind of function? It's a sine hyperbolic function. Okay, so the shape of the curve is cosine hyperbolic. The length of the curve is a sine hyperbolic. And finally, you might say, what about the tension in the cable? Well, let's take a look. Here, we consider this portion of the cable, whereas it's on the left, it's cut at the very bottom of the cable. On the right, it's cut at distance x. So this is not an infinitesimal part of the cable. This is like a considerable part of the cable, depending on how much x is. And at this very bottom point, the tension is, of course, horizontal, and we call it T naught. At this other end, we call it T, which is not constant. It's a function of x, and this theta is also a function of x, the slope. And the total weight of this portion of the cable is mu times s downward. Now, any portion of this cable has to be at equilibrium, including this guy. So here there are three forces, T, T naught, and mu s, and these three forces have to be at equilibrium. So clearly they should form a what? They should form a right triangle like this. So you have this one, you have this one, and you have this one. This is your T, this is your mu times s, and this is T naught. And clearly you see that mu s squared plus T naught squared is equal to T squared. You factor out a T naught squared from both sides, you get this one. Now you might say, what is this mu s over T naught? The whole thing is squared. For that, I need to go back to the relation I found earlier, and that was dy over dx, or p, or tangent theta. It was mu s over T naught, right? And you can see that from this triangle too. If you look at this triangle, this angle here is theta. And tangent of theta is mu s over what? T naught. And remember, tangent theta is the first derivative. So, and remember the first derivative was a sine hyperbolic function. So if I replace these two here for this square term, I use what? I use this sine hyperbolic term. And again, remember 1 plus sine hyperbolic is a cosine hyperbolic. So it becomes like that. Take a square root from both sides, and tension becomes a cosine hyperbolic function. So tension in the rope at any point is a cosine hyperbolic function. And of course, it's a function of x, and cosine hyperbolic is an increasing function of x, right? So when x gets bigger, this cosine hyperbolic gets bigger. So the maximum tension is where x is maximum, and x is maximum at L over 2. So at this point and at this point, you have maximum tension, and that maximum tension is this function that you can see. So if I want to summarize everything, for a cable under its own weight hanging from 2 points, the shape of the curve is cosine hyperbolic, as well as the tension in the rope, but the slope, as you can see, the slope here, this guy, as well as the length of the cable are what? Sine hyperbolic functions. So there we go. You can see sine hyperbolic and cosine hyperbolic in real life. So hopefully this video was useful to you, and I'll see you in the next lecture. Thank you.